So standard position represents the location or position, and it's denoted by x of t. You may see it as s of t, so I'm just going to write an or, and then you can go ahead and write in s of t. You might see it this way, but most of the time you'll see it as x of t. Our velocity function represents constant speed with direction, and that is v of t. Now, v of t is the first derivative of x of t. So the derivative of standard position is velocity. Our acceleration function represents change in velocity over time, and our acceleration function is x double prime, or the second derivative of x of t, or the first derivative of v of t. So basically, to get the velocity, you take the derivative of standard position, and to take the acceleration, you take the derivative of velocity. Okay, so let's just talk about all this stuff in context with a problem. So it says, Miss Mangine throws a ball in the air. The height of the ball is modeled by this function, x of t, where t is measured in seconds, and s is the height of the ball from the ground in meters. It should say x of t, not x. So x of t is the height of the ball from the ground in meters. The graph of x of t is given below here. So first, what is the initial height of the ball? So we know that height is your x of t. It tells you x of t is your height. So if I want to find the initial height, I want to know at time equals 0. The word initial means starting height, not height after 1 second. So don't confuse that for being 1. Initial means in the very, very beginning. So if I want to find that, all I'm going to do is plug 0 into my x of t function. So negative 4.9, 0 squared, plus 18 times 0, plus 2. Now we can clearly see that this is 0, so the answer is just 2. So if we want to put it in context to the problem, we should be saying meters. So 2 meters tall. That's the initial height. And that makes sense, right? I'm going to throw a ball in the air. I'm not starting at the ground level. I'm starting 2 meters off the ground, which is likely my height. What is the initial velocity of the ball? So initial velocity still, again, means time equals 0, but this time we're going to plug it into the velocity function. Well, we don't have velocity. We have the standard position, or the height. So in order to find velocity, we have to know that velocity, v of t, is the derivative of x of t. So we're going to use a simple power rule. So negative 4.9 times 2, that'll give you negative 9.8. And decrease the power by 1. So 2 minus 1 is 1. And the derivative of 18t is just 18. And the derivative of 2 is nothing. So that's my velocity function. We're going to plug 0 in now. So negative 9.8, plug in 0, plus 18. This time 0 goes away, so my v of 0 is just 18. Now we need units. So if we look up here, velocity, we said, is a constant speed with direction. So think of a car, miles per hour. So what do we have here? We have seconds and meters. So we're going to say 18 meters per second. That's the speed at which the ball will be thrown. When is the ball at rest? Well, the ball being at rest, that's an interesting concept. If I'm throwing a ball, some of you might think, well, how could it ever be at rest? And I want to just show you the graph down here. This is the graph of me throwing the ball. So here I'm a little off the ground, I throw it. Now up here is called a turning point, or the vertex, right? So at this split second, right before it goes and starts traveling down, the particle is technically at rest. And that occurs when my velocity, my v of t, is equal to 0. So there's no speed. So if you really slow it down and you throw the ball up, at that split second before it goes down, it's pausing and there's no speed there. So we need to set our v of t function, which we just found here, equal to 0. So the 0 is going in for v of t right here. So 0 equals negative 9.8t plus 18. We can minus 18 on both sides. So negative 18 equals negative 9.8t. And then we can divide both sides by negative 9.8. Now trust my math on this. You should get t is equal to 1.836 approximately. So at that specific spot, that is when I am at rest. Now you can kind of see here, right? Well, I talked about it. This is where it's the vertex. It's not exactly 2. It's probably a little here, which is 1.836, right? Between 1 and 2. That makes sense. Okay, so the next part, they say, when is the ball's velocity positive and when is it negative? So in order to answer this question, we have to understand that since velocity is the derivative of position, we can look at the slope of the position to help us find velocity, right? Because slope means derivative. So we have a positive velocity when x of t has a positive slope. We have a negative velocity, I'll put v of t instead. We have a negative velocity when x of t has a negative slope. So to answer the question, let's look at the graph. So a positive slope occurs all the way up until we are at this vertex, and then a negative slope occurs all the way down. So we would say positive slope from 0 to about this 1.8 that we got here. So positive from 0 to 1.836, and a negative slope from 1.836 to about when it hits the ground here. So I'm estimating when it hits the ground. I probably should have had another section here to ask you where it is hitting the ground. So we'll just assume that it hits it around 4, but really there is a way that we can find that, and I can talk about that a little bit more tomorrow. So we'll adjust and estimate and say that's about 4, okay? So the next part says, draw a sketch of these graphs. Well, we have a sketch of position. We now need a sketch of velocity. So we need to know where velocity starts initially. So I think we did that. It initially starts, initial velocity at 18. So we're going to start our velocity graph at 18. So somewhere between 15 and 20. Now we know that we have a positive velocity from here to about here. And then the velocity or the ball is at rest at 1.836 or up here. So v of t equaling 0 means that that's where it's going to equal 0. So 1.836 is where my velocity is 0. So all we're going to do now is go and connect this value and keep going down. So that is my velocity function. All right. And it makes sense too. Isn't this like a negative x squared graph? So, you could estimate and just say, okay, this is like a negative x squared-ish. And the derivative of that is negative 2x. Isn't that a line, right? So it's a negative line. It makes sense. And then what's the derivative of a negative 2x? Just 2 if we keep going. So the acceleration function should be constant. And I think we already had that, right? Did I find that? No, I didn't. Okay, so let's find the acceleration function and see what it is. So remember, acceleration is the derivative of velocity. So if I write a of t over here, negative 9.8t plus 18. Well, the derivative of this term is negative 9.8, so negative 9.8, and the derivative of 18 goes away. So my acceleration function is that constant. So simply negative 9.8. So that would be somewhere here, and just this horizontal line would be my acceleration function. Okay. Let's move on to the back. Okay, last thing I want to talk about is how we can apply motion with a particle moving along a horizontal line. So there's two key concepts here, displacement and distance. Displacement is the difference between the ending position and the starting position. And the distance is the total amount covered. The way that we can find the displacement is literally take the difference or subtract the starting value or the ending value and the starting value over this interval. And the way we find the distance is just by adding everything up from start to finish. So it makes sense if I show you an example. So here is a diagram of a particle moving along a horizontal line. Now, the way that I draw it, it looks like the particle is going up and over and up and over. But the real thing that's happening, I need you to understand, is we have a particle that's going like right, then left, then right, then left, and it's all horizontal and like going on top of each other on that same line, and that's very difficult to draw. Okay, so what's happening? Let's analyze. At time equals 0, I'm here, and I'm moving to the right, then I'm going back to the left, and then I'm going to the right. This line down here is your standard position. This is where I'm located. So x of t, this is my location on the line. What function, x of t, v of t, or a of t, tells us position or location? And the answer is x of t. The x of t function will always give us our location. So let's go to the next part. Where is the particle located at time equals 0 seconds? Well, at 0 seconds, time is 0, not this 0. Time is 0. I am located at -2 on that horizontal line. So at time equals 0, location is -2. And what that corresponds to is x of 0 equals -2. So the standard position gives us where we are located. At 12 seconds, so at time equals 12, my location is what? Let's see. So at time equals 12, my location is 10. So that corresponds to x of 12. At time equals 12, I am at 10 on that horizontal line. So part C, what is the displacement covered from 0 to 12? So remember, displacement is how far away you are from the starting value when you end. So the formula, this is your A and this is your B. They're giving you an interval from 0 seconds to 12 seconds. The formula, the formal definition, is x of B minus x of A. So since B is 12, we would subtract x of 12 minus x of 0. And x of 12, we just found out. That is where I'm located at time equals 12. That location, when time was 12, I was located at 10. And x of 0, we found out that when I'm at 0 time, I'm located at -2. So 10 minus double negative here, -2, this total displacement is 12. But what does that mean? A displacement of 12 means, since it's positive, let's write down what it means and then confirm it. A positive displacement means the particle ended 12 units to the right of where it started. And if it was a -12 here, the particle would have ended 12 units to the left of where it started. So let's see if this makes sense. At time equals 0, I'm at -2, and at time equals 12, I'm at 10. So do you see how this is where the particle, if you want to even label it, this is where the particle started, and this is where the particle ended. So clearly, from the start, -2, to the end, 10, if you do some math here, there's 2 units from -2 to 0, and 10 units from 0 to 10. So this total distance here is 12. So it ended 12 units to the right of where it started. Now, the last part is, what is the total distance covered over this interval? So in order to find the distance, we actually have to add up all of these segments separately. Otherwise, there's no way to do it, right? We have to just break it down. So let's do that. So what's the distance, you want to ask yourself, from 0 to 4. Time equals 0 to time equals 4. Well, I started at -2 and I wound up at 30. So again, use 0 as your marker. From -2 to 0 is 2 units, and from 0 to 30 is another 30. So this distance here is 32. So now let's keep going. What if I want to know from time equals 4 to time equals 8? Well, time equals 4, we are at 30. And then at time equals 8, we're at -10. So from 30 to 0 is 30. Add 10 more, that's 40. And then the last segment is here. So say I want to go from time equals 8 to time equals 12. So I'm going from -10 to +10. So -10 to 0 is 10. And then 0 to another is another 10, so 20. So this distance here would be 20. So if I want the total distance, I'm just going to add up the 20, the 40, and the 32. So 20 plus 40 plus 32 is equal to 96 units.